just like the last video, this one is optional. Well, I guess they're all optional. I can't make you watch them. But this one is only recommended if you feel like you need a brush up on partial fraction decompositions. So if you feel comfortable with that algebra, skip this video, move on to the next one. Okay. In the last video, we took a look at the linear factor rule for partial fractions. So in this, we're going to take a look at the irreducible quadratic factor rule. Okay. So I didn't write out all the details here, but remember what we do is we factor the denominator completely. Now, over the real numbers, everything can be factored completely into linear and irreducible quadratic factors. So if you got a cubic, it factors. Keep working on it. Okay. Once you've done that, we're going to consolidate all of the like factors. So if I had two factors of x minus 1, rather than writing x minus 1, I'd write it as x minus 1 squared. Once we've done that, every factor in the denominator of this form, ax squared plus bx plus c, where that's an irreducible quadratic, so it does not factor over the real numbers, raised to a power of k. So obviously k will be a positive integer, okay? If it's to the kth power, it's going to contribute k fractions. We've still got that rule that the number of factors matches the number of fractions. Now, it's possible that the fractions, when we solve for the coefficients on top, will get zeros, and so some of the fractions will disappear. But in the general form, before I solve for those constants, k factors, k fractions. Okay, and what do they look like? Well, the denominators will just be that irreducible quadratic and its powers. So, if it appears just once, we get the denominator of ax squared plus bx plus c. If it appears twice in the denominator, we get a second fraction with ax squared plus bx plus c squared in the denominator. And we keep going. If it appears k times, we're going to have k fractions, and the power of that irreducible quadratic in the denominator just goes up one each time until the last one has the kth power. All of the numerators are just linear functions. Linear functions are just some x's plus a number. Okay? So, if I were to have something like 5x plus 1 over x squared plus 4 times x minus 1. Now, x squared plus 4 is an irreducible quadratic. Does not factor over the real numbers. And obviously, this is a linear factor. So I've got two factors. So I'm going to have two fractions. One will have x squared plus 4 in the denominator, and one will have x minus 1. For the x squared plus 4, that's an irreducible quadratic, so I get a linear on top, some x's plus a number. This is a linear, so I get just a constant on the top. Okay. So that's the general form there. If I had something like 3x squared minus 5x plus 2 over x squared plus 4 squared, now that's a repeated irreducible quadratic. So that's two factors. So again, I'm going to have two fractions, x squared plus 4 and x squared plus 4 squared. If it's an irreducible quadratic or a power of 1, the top is just linear. So it'll be ax plus b, cx plus d. Okay, I've got the same two options for figuring out what these numbers are on top. I can plug in numbers for x and then solve for the unknown constants, or I can multiply things out and equate like coefficients. Okay. So, what I often do, I'm going to just illustrate with this example, I will often mix the two techniques. So if I have this, and I'm trying to solve for a, b, and c, first thing I would do is multiply by this, the least common denominator, to clear all of those denominators. So when I do that, I'm going to get 5x plus 1 equals here, the x squared plus 4 will cancel, but I'll have ax plus b being multiplied by x minus 1. And here the x minus 1 will cancel, but I'll have c times x squared plus 4. Do be careful. Anytime you have something with more than one term, make sure you put it in parentheses. Okay. Now, I do have one value for x that it's really convenient to plug in. If I let x equal 1, that's going to kill off this term and make it really easy to solve for c. So I'm going to start with that. If x is 1, this is 5 plus 1 is 6, is equal to this term gets killed off, this term becomes 1 plus 4 is 5 copies of C. So that tells me that C is 6/5. Now, I don't have any other convenient numbers to plug in because there's no real number that's going to make that 0. If it doesn't factor, it doesn't have any real roots. So, for the rest of it, I'm going to just multiply things out to equate like coefficients. So I've got 5x plus 1 is, we'll FOIL that out. So ax squared minus ax plus bx minus b. Plus, now I'm going to distribute the c here, but I know that c is 6/5. So let's go ahead and plug that in. So plus 6/5 x squared plus 24/5. So now let's consolidate. I've got 5x plus 1. The number of x squareds I have is a plus 6/5. If I take a look at the number of x's that I have, looks like that's here and here. That's going to give me negative a plus b copies of x. And if I take a look at my constants, looks like that's this term and this term. So that's going to be plus a negative b plus 24/5. All right. Now, if I look at the types of terms that show up on either side of this equation, I have 3 types of terms still. I've got x squareds and x's and numbers. Okay. But I'm only solving for 2 things, a and b. So 2 of the 3 equations I get are going to be enough for me to solve for all of my unknowns because I already know c. That's one thing I kind of like about doing it this way. There's a little bit of redundancy built in. If I use the first 2 equations to get a and b, and then that makes the 3rd equation false, I'm going to know I made a mistake somewhere in my arithmetic so I can go back and look for it. Whereas if the 3rd equation is true, then doesn't mean I didn't make a mistake, but it means it's less likely that I made a mistake, so I feel a little bit more confident moving forward. Okay, so if we look at the x squareds, on the left, I have none. On the right, I have a plus 6/5. So that's nice. A is negative 6/5. Now if I look at the x's, on the left I have 5 of them. On the right I have negative a plus b. But I just figured out what a was. So a was negative 6/5. The opposite of that is going to be 6/5. So we've got 5 is equal to 6/5 plus b. That's 25/5 equals 6/5 plus b. So b would just equal 19/5. So let's see, I've got c equals 6/5, a is negative 6/5, and b is 19/5. Let's just see if that works in this 3rd equation. Okay. I could just move on and say, hey, I've got my a, b, and c, but it's going to be a quick check to make sure that that works here, and if I've made a careless mistake, that's going to catch many of the careless mistakes I might have made. Not guaranteed to catch all of them. There's so many mistakes women make. Okay, so the constant term here is 1. We said here it was going to be the opposite of b plus 24/5. So that would be the opposite of 19/5 plus 24/5. That would be 5/5, and that checks. So now I'm going to move on, if I were actually doing this problem, and feel a little bit more confident that I got the right values for a, b, and c. Okay, we'll see plenty more of partial fractions as we work through the Laplace transforms. But I did want to just take this time out for any of you who did feel that you needed to just review that algebra. Okay, so we've got that. Back to Laplace transforms.